1. A coaxial cable is a kind of data cable that has a central wire, an outer sheath, and sometimes a region of insulation between. Current flows in one direction in the central wire and the other direction in the outer sheath. In the coaxial cable below, the central wire and the outer sheath each carry a current of 2 milliamperes, and the middle insulation carries no current. Find the magnetic field at R equals 2 millimeters, R equals 4 millimeters, and R equals 5 millimeters. Please pause the video to attempt this problem. So we want to find the magnetic field at 3 different distances, so we will need to solve this problem 3 different times. So the first time, we want the magnetic field at 2 millimeters. Now consider the inner wire has a radius of 3 millimeters. So for this, we are looking at the situation where we want the magnetic field inside an infinite wire. So because of that, and we are also completely ignoring the outer sheath entirely, because that outer sheath is again outside of our Amperian loop. So we can go ahead and use this formula right here. If we are inside an infinite wire, the magnetic field is equal to mu sub naught over 2 pi times the total current in that wire times the distance, the radius that we're looking at, divided by the square of the radius of the wire. So plugging that in, we've got mu sub naught, which is 4 pi times 10 to the negative 7th Tesla meters per ampere over 2 pi. I, that is the current just in this inner wire of 2 milliamperes, or 2 times 10 to the negative 3rd amperes. Little r, that is this 2 millimeters. That is how far from the center we are. So 2 times 10 to the negative 3rd meters, divided by big R squared, big R being the total radius of this wire. Again, we're completely ignoring the outer sheath. Big R is 3 millimeters, or 3 times 10 to the negative 3rd meters. And if you plug that in, the answer you get is 8.9 times 10 to the negative 8th Tesla, or 89 nanotesla. Part B, what is the magnetic field at 4 millimeters? Well, looking at this diagram again, 4 millimeters is completely outside of the radius of the inner wire, and it's just before we start hitting the outer sheath, which means that our Amperian loop at 4 millimeters will encompass all of the current in the inner wire and none of the current of the outer wire. So because we have our current completely enclosed, we can go ahead and use this formula right here, mu sub naught over 2 pi times I over r, plug in our values, and we get that at that distance, the magnetic field is 10 to the negative 7th Tesla, or 100 nanotesla. Lastly, looking at the magnetic field at R equals 5 millimeters. Well, consider now that we're out at 5 millimeters, we have both the inner cable and the outer sheath that we have to look at their currents. The inner cable has a current of 2 milliamperes. The outer sheath has a current of 2 milliamperes, but they're both going in the same direction, which means the total enclosed current of a 5 millimeter radius Amperian loop is 0, which means the magnetic field will be 0. As a side note, this is the main purpose of coaxial cable to begin with, is that it does not create a magnetic field outside of the wire, or at least in a real situation, it creates very, very little magnetic field. It turns out that rapidly creating and removing magnetic field makes it difficult to send electricity in general and data in particular through the wire. Problem 2. 2 parallel infinite plates carrying current. There are 2 parallel infinite plates carrying current. Both plates have the same magnitude of current density, which we can call lambda. For the top plate, the current is going into the page, and the bottom plate, the current is coming out of the page. what is the magnitude of magnetic field everywhere? Please pause the video to attempt this problem. So we saw the magnetic field created by a single infinite sheet. That's not necessarily two infinite sheets. However, we can, again, use the principle of superposition to determine the magnetic field of two infinite sheets by finding the magnetic field of each sheet individually and combining them. So for the top sheet, the current is going into the page, which means that we can use the right-hand rule and say that above this wire, or above this plate, the magnetic field is going, point our thumb into the page, stick our fingers up, and then curl them, and you can see they curl to the right. So this sheet creates magnetic field to the right above it and to the left below it. This plate has the current coming out of the page, so if we hold our thumb pointing towards us, point our fingers up, and then curl them, we can see that above this wire, the magnetic field is going to the left, and below it, it's going to the right. Also recall from our formula that the magnetic field depends solely on lambda, does not depend on how far away you are from the sheet. So both of these sheets will create magnetic fields that have magnitude B is equal to mu sub naught lambda over 2. Now, if we think about the directions, in this region that's above both sheets, this top sheet is making the magnetic field go to the right, this bottom sheet is making the magnetic field go to the left. They will cancel out up here. Below both sheets, the top sheet is making a magnetic field that's going to the left, the bottom sheet is making a magnetic field that goes to the right. They will, again, cancel. It's only in the middle. The top sheet makes a magnetic field going to the left. The bottom sheet makes a magnetic field going to the left. In the middle, they will add together. And so the total magnetic field is equal to mu sub naught lambda over 2 from the top sheet plus mu sub naught lambda over 2 from the bottom sheet, or just mu sub naught lambda. Now, this problem should be setting off some memories, because this looks an awful lot like the capacitor problems that we dealt with in electric circuits. Remember that for the next lecture.